So the second question asks us to determine the expression for the charge dq of the ring with a thickness dx in terms of the known variables. So we know that the distribution of charge is constant throughout the cylinder, so we can set up this proportion right over here. So a proportion of charge over the total charge is equivalent to the area of that portion over the total area. So in this case, because we're taking the area of a surface of a cylinder multiplied by however long the ring is, which is dx, so we can simplify accordingly. And so dA becomes and it's just asking us to find the relative position vector r, which is the thickness from the center of the slice to the location over W. A, which is 2 pi r times the length of the cylinder itself. And so when we solve for dq, we actually get from the source equal to q the observation location. And dx. So to do that, you do observation location minus source. And then you subtract the vectors and you get this as your relative position vector. So the second question asks us to determine the expression for the charge dq of the ring with a thickness dx in terms of the known variables. So we know that the distribution of charge is constant throughout the cylinder, so we can set up this proportion right over here. So a proportion of charge over the total charge is equivalent to the area of that portion over the total area. So in this case, because we're taking the area of a surface of a cylinder multiplied by however long the ring is, which is dx, we can simplify accordingly. And so dA becomes 2 pi r dx, which is the thickness of the ring, over A, which is 2 pi r times the length of the cylinder itself. And so when we solve for dq, we actually get dq is equal to q over L times dx. So the next part asks us to write an expression for the electric field dE made by the ring at location W using results from both part A and B. So based off on our formula sheet, you're given the equation for the electric field produced by a ring. So you write that down, and the biggest thing to consider is that in place of Q, you'll be using dQ to represent a portion of a portion of the charge, which will produce a certain portion of the electric field. So we're able to substitute Q for dQ. The next important part is actually finding an expression for the relative position vector that is in terms of x and w. So in order to accommodate for the amount of charge on a ring of thickness dx from the previous problem. So to find that expression, you essentially have to use the distance formula. Once you have an expression for the relative position vector, we can substitute it back into our equation for a portion of the electric field. And we can also substitute the expression for dq as well, which is q over L. Now the last part asks us to determine the net electric field at location W. So in order to do this, in order to get the net field, you'll have to take the integral. So you'll be integrating over the length of the cylinder, which if we look back at that graph or that diagram is actually from negative L over 2 to L over 2, and using the previous equation that we got for the electric field in the x direction. And so the easiest way to integrate is actually using u substitution. So if we set u equal to w minus x squared plus r squared and then take the derivative of this expression, then we can change the boundaries accordingly and integrate with a little bit more ease to give us a final answer.